this is part 2 of the problems on the wave nature of light. We are starting from problem number 9, which is listed as 1 here. Suppose that doesn't matter. A single slit 1 millimeter wide is illuminated by 450 nanometer light. What is the width of the central maximum in the diffraction pattern on a screen 5 meters away? What is important is to remember that the conditions for brightness and darkness are switched in the case of a single slit diffraction pattern. And here you're asked to find the width of the central maximum. Now what do you have at the edge of the central maximum? You have darkness, right? Because you have a central maximum and you have darkness at the edge. So we have to use the condition for minimum here. And the condition for minimum in this case is the condition for maximum in the interference of two slits, right? So the condition for minimum is what we're going to use. The width of the central maximum is going to be twice the distance from the center to the first minimum. And sine theta 1, as we have seen, is lambda by d, where caps d is the distance of the slit from the screen. Therefore, you can find the angle. Lambda is 450 nanometers. And you have the distance to the screen as, the distance of the slit. I'm sorry, that is the distance. The caps d is the distance of the width of the slit, rather. The width of the slit. All right, the width of the slit is 1 millimeter. That's why it's 1 times 10 to the negative 3, and you get that angle. And here I'm trying to explain that that's the central point on the screen. This is your first minimum. And if this angle is theta 1, which is what we found out from this right angle triangle, you know y1 is L tan theta 1. Okay. And the L is the distance to the screen, which is 5 meters. When you do that, you get y1 in meters, and the width is actually twice that. And remember that the reason why it's twice that is because you have the same phenomenon here, and that is actually the central maximum, the width of the central maximum. Okay. This question talks about a slit diffracting 580 nanometer light so that the diffraction maximum is 6 centimeters wide. So that's again talking about the central maximum. And the screen is 2.20 meters away. What will be the width of the diffraction maximum for light of wavelength 460 nanometer? That's a comparison problem. You could just set it up as a ratio. From the last problem, we saw y1 is L tan theta 1. And y1 is actually half of the width of the central maximum. Remember that? y1 was half. Okay, because delta y1 here is the width of the central maximum. It's given us 0.06 meters, so that's 0.03, from which you can find theta 1. Make theta 1 the subject and substitute, you get the angle, it's 0.781 degree. Therefore, sine theta 1 is lambda 1 by caps d, and that gives you d as lambda 1 by sine theta 1. Lambda is 580 nanometer. I'm going to leave it like that because it's a ratio question. That gives 42,537 nanometer as the width of the slit. Now we can use that information in the second one to find sine theta 2, because the second wavelength is 460 nanometers. Now I'll have to use that and then take twice that. Actually, I have not calculated because there's no space here. You'll have to take twice of that. I think you can get the answer, right, with that? And this is question number 11, which is 4 here. The question numbers do not tally, but it's the 11th question. How many lines per centimeter does a grating have if the third order occurs at an 15-degree angle for light of wavelength 650 nanometer? Now, for a grating, the condition for maxima and minima, we go back to the same thing as for a double slit. So it's only for a single slit that it's reversed. So here we're talking about a grating. You have to remember the formula for a grating. D sine theta is equal to m lambda, condition for brightness. And remember that the number of lines in 1 meter is 1 by d, where d is the width of one slit. So when you substitute that here, you get nm lambda. All you have to do is just remember this formula, which is a really important one. Sine theta is nm lambda. And what's n here? N is the number of lines in 1 meter. M is the order of the spectrum. Lambda is the wavelength. So from this one, n is this, because in this question you're asked to find how many lines per centimeter. We're going to get it in meter first. Just a matter of plugging in those numbers, and you have 1300 lines per centimeter, which means, okay, what is that? All right, per centimeter, and yeah, that's what it's asking you. So that's why I changed this to 10 to the negative 7, so I would get the answer per centimeter, okay? Otherwise, it should have been 10 to the negative 9. So I changed it to 10 to the negative 7, and I directly got 1300 lines per centimeter. In this question, again talking about a diffraction grating, the number of lines per meter is given, and you have to find the angular spread in the second order spectrum. So m is 2, and there are 2 wavelengths. You have to find the difference in the angles at which they are produced. So first find the angle for one of them, do the same for the second, take the difference. This is the formula basically for the grating. Make angle the subject. And you know that 1 by d here is n, right? That's why it's n here, number of lines per meter. Find the angle for this wavelength, 4.5 times 10 to the negative 7. Get it as 32.7 degrees, and do the same for the second one, which you get to be slightly bigger than that, definitely, because the wavelength is greater. You get 57.1, and then take the difference between the two, which gives you 57.1 minus 32.7. That's 24 degrees is the angular difference in the second order spectrum between these two wavelengths. Oh, on to polarization now. This is question number 13 on your problem set. 2 polarizers are oriented at 36 degrees to one another. Light polarized at an 18-degree angle to each polarizer passes through both. What is the transmitted intensity? It's polarized light that's falling on the first one. You should remember that. And the first angle between the light and the polarizer is 18 degrees. But for the second one, because it's oriented at 36 degrees to the first one, the angle between the light and polarizer is 36 degrees. And using Malus law, I1 is I0 cos squared 18, where I1 is the intensity that passes out through the first one. And then for the second one, it's going to be I1, because it's I1 that's passing out through the second one, right? So you get 0.592 I0. So that means it's 59.2% of the initial intensity. That must be clear. And this question, it talks about unpolarized light. This unpolarized light, now in this case, passing through 6 successive polarized sheets, each of whose axis makes a 45-degree angle with the previous one. Okay, there are 6 Polaroids now. And by Malus law, intensity is I0 cos squared theta. Theta is 45 degrees. Cos squared 45 will be 1 by 2. And from sheets 2 to 6, the intensity reduces by 50%, by half. But remember that sheet 1 itself will cut down the intensity by 1/2. Because when unpolarized light passes through the first one, already the intensity is cut down by half. So totally, you have half raised to 6. And the final intensity is 1.6%. Just remember that the first sheet always reduces the intensity by 50%. But then what happens on the second and the third and so on depends on the angle. But for the first one, it's always reduced by 50%. That's a very important point. Brings us to the last one. Show that when light is incident at the polarizing angle, the reflected and refracted beams are perpendicular to each other. So light is incident, partly reflected and partly refracted. And we are having to show that this angle here is 90 degrees if the light is incident at polarizing angle. So if that is the polarizing angle, theta I, you know this should also be theta I, because the angle of incidence is equal to the angle of reflection. And this is theta R, angle of refraction. Well, this can be proved just by using 2 laws. One is the Snell's law and the other is Brewster's law. So the refractive indices are N1 and N2. That's kind of very slow writing now, so let me speed that up. Snell's law, N1 sine theta I is equal to N2 sine theta R. Okay, now what is Brewster's law? Tan theta I, or tan theta P, is actually equal to N2 by N1. Okay, so rearrange that. You know, tan is nothing but sine by cos, so I've written that as sine by cos and cross multiplied to get number 2. Look at 1 and 2, the left hand sides are equal, so the right hand sides may be put equal to each other. The N2s are cancelled, so that means sine theta R is equal to cos theta I, and theta I can be written as, on the side cos can be written as sine 90 minus theta. So that shows that this angle is 90 degrees because the total angle is 180 degrees, right? We proved that theta I plus theta R is 90, and since the total angle is 180, the remaining angle has to be 90. So the the reflected and the refracted beams are perpendicular to each other. Thank you.